Hello everyone, I'm Thomas Hogan and I'll be presenting the final presentation for ECE 6013, Overview of Oceanic Wave Energy Conversion. We will start by presenting an overview of various means to classify wave energy converters, then discuss the fundamental assumptions in linear wave theory to develop the harmonic wave. The hydrodynamic forces will then be established in the frequency domain, describing their physical significance. We will then move to the time domain and discuss the Cummins equation, paying particular attention to the radiation and excitation forces and introducing Morrison's equation. The energy maximizing conditions will be established in the frequency domain with complex conjugate control, followed by the corresponding formulation in the time domain, impedance matching. Three distinct control schemes will then be evaluated. Finally, a generic power conversion chain will be presented, followed by an overview of direct drive linear generators. The elements in this to be presented correspond directly in order and are grouped as in the rubric. Ocean wave energy has the potential to contribute to meeting the demand of increasing electrification. It contains the highest energy density compared to other renewable sources such as wind and solar, while also being much more predictable and making it an appealing alternative. Furthermore, diversifying energy generation by including additional renewable energy sources can help ease the inevitable transition from fossil fuels to more sustainable methods. However, WECs are still in their technological infancy and their levelized cost of energy is not yet competitive with other renewable energy sources. Wave energy is extracted from ocean waves, particularly surface gravity wind waves. These waves are generated by wind acting over the ocean surface and have temporal periods ranging from half a second to 30 seconds. The global theoretical resource is estimated to be in the range of 2 to 3 terawatts, of which 0.4 to 1 terawatt is estimated to be recoverable. Comparing this to the global electricity demand as of 2019, which was 2.6 terawatts, should the entire recoverable wave energy resource be captured, upwards of 15 to 40% of the world's current electricity demand could be satisfied. Although fully extracting the exploitable resource is unrealistic, even a fraction of this total could supplement existing generation sources and further decrease reliance on fossil fuels. A simplified view of a typical WEC environment contains various important characteristics. The incident wave is the incoming wave, shown here as a one-dimensional, unidirectional, monochromatic surface gravity wave propagating in the rightward direction, where the topmost point on the wave is the crest, the lowest is the trough, and the distance between the two is the wave height. The distance between the trough or the crest and the undisturbed sea surface is the wave amplitude, and the distance between any two like points on consecutive waves is the wavelength. All WECs, regardless of design, contain four common subsystems: hydrodynamic, power takeoff, reaction, and control. The hydrodynamic subsystem describes the fluid body interaction between the WEC and the incident wave. The PTO subsystem takes the captured energy from the hydrodynamic subsystem and converts the mechanical energy into a more useful form. The reaction subsystem describes the means of station keeping or mooring of the WEC, and the instrumentation subsystem refers to the intelligent operations of the device. Classification according to size and orientation refers to the size and position of the device relative to the incident wave. This system defines three distinct device categories: terminator, attenuator, and point absorber, whose geometries and dimensions can be seen here. Terminators have their largest cross-section parallel to the incident wave. Alternatively, attenuators have the largest cross-section orthogonal to the wave. Meanwhile, point absorbers are small relative to the incident wave. Classification according to working principle refers to how the device captures energy. This system defines three distinct device categories: overtopping, oscillating water column, and wave-activated body, whose geometries and dimensions can be seen. An overtopping device captures energy by allowing waves to break over a sloped wall into a reservoir stationed above sea level. The water exits through an outlet at the bottom of the reservoir where a low head water turbine is positioned. An oscillating water column uses the oscillation of water levels within a chamber to capture energy by creating a pressure differential between the air in the chamber and the environment. It uses an air turbine, often a Wells turbine, stationed in the port, which can extract energy from the bidirectional airflow. The description of wave-activated bodies covers a diverse range of devices. However, the overall working principle is consistent throughout. They use the incident wave to excite a body into oscillatory motion that reacts against a reference point, whether that be another body or a fixed point on the seafloor. The interaction between the wave and the body extracts kinetic energy from the wave and converts into the kinetic energy in the form of oscillatory motion of the body. Linear wave theory, otherwise known as Airy wave theory, provides a means to describe fluid flow in idealized conditions. Complex waves can be represented as the superposition of independent harmonic waves, with each representing a propagating wave of constant frequency and small and constant amplitude. Selecting idealized kinematic boundary conditions and enforcing various assumptions, the harmonic wave can be found as an analytical solution to the Laplace equation. First, we will define the velocity vector field u, which is equal to the spatial derivatives of the velocity potential function phi. Potential flow theory assumes steady state, continuous, ideal fluid flow, meaning it is incompressible, irrotational, and viscid and has a constant density. The assumption of incompressibility implies that the water particles cannot be compressed and is imposed mathematically by the divergence of the velocity vector field being zero. Similarly, irrotational refers to there is no shearing on the water particles that would cause it to rotate about its axis and is represented by the curl of the velocity vector field being zero. The continuity equation arises when the constant density assumption is applied to the mass balance equation, and when it is written in terms of the velocity potential function, the Laplace equation arises. Furthermore, a vector field is conservative if a given potential function satisfies the Laplace equation, meaning the vector field is path independent and must be the case in this formulation. Idealized boundary conditions must be applied to the Laplace equation to determine a unique solution. Only the kinematic boundary conditions at the free surface and seafloor will be considered. The kinematic boundary condition evaluated at the undisturbed water level imposes that the velocity of the water particle normal to the surface is equal to the surface velocity, or in layman's terms, the particle remains within the surface. Now considering the kinematic boundary condition on the seafloor, evaluated at a depth of h, that states the fluid particles are unable to pass through the horizontal seabed. The boundary conditions have been defined, and now applying them to the Laplace equation gives rise to the general form of the velocity potential, and is represented mathematically by an exponential, suggesting that it decreases with depth in the form of a decaying envelope, where g is a constant, k is the wave number, and omega is the wave frequency. The harmonic wave equation results as one of the analytical solutions to the Laplace equation, where a is the wave amplitude. Frequency domain models are valuable because they provide context behind the hydrodynamic forces and they're inherently linear, corresponding to a series of algebraic equations rather than differential equations. However, the linearization process requires implementing oversimplified models, limiting their accuracy. Moreover, frequency domain modeling inherently only models steady-state conditions along with harmonic and small amplitude wave motion. Furthermore, representations in the frequency domain rely on a simplified lumped parameter mass spring damper model with linear time invariant coefficients to represent the WEC. Considered in this derivation is a single body constrained to motion and heave and impedance defined relative to velocity. The forces will be decomposed as we progress through a tree chart, starting with Newton's second law. The device velocity vector u is the real component of the complex velocity amplitude big U. Writing this displacement vector exclusively as a function of time implicitly assumes it is a linear harmonic function of constant frequency, and differentiation in the time domain corresponds to multiplication by I omega in the frequency domain, meaning that position and acceleration can be represented similarly. Newton's second law, including the forces acting on the WEC, as detailed in the time domain, is represented by the mass of the WEC m, the force due to external pressure F sub Pe, and the reaction force F sub Re. This can be obtained in the frequency domain by taking its Fourier transform. The force from external pressure can be represented as the summation of the force from hydrodynamic F sub Hd and hydrostatic F sub H. The hydrodynamic refers to the dynamic force acting on the WEC, while the hydrostatic force is the restoring force between gravity and buoyancy. Per Archimedes' principle, when the object is at rest, the buoyancy force and the force of gravity are balanced. Should the object be displaced from its equilibrium position, a restoring force will be applied to bring the device back into equilibrium. In reality, this is represented by the surface integral of the hydrostatic pressure on the wetted surface of the hull in undisturbed conditions, but can be simplified to a hydrostatic stiffness K sub I. But this assumes a constant water density, small amplitude motions, and a constant cross-sectional area, S. The hydrodynamic force is comprised of an excitation, F sub E, force, which describes the external force on the system arising from the pressure on the wetted surface of the hull, from the incident wave when the body is held fixed, along with a radiation force, F sub R, that details the force generated from the oscillatory motions of the WEC in otherwise calm waters. This force is represented by the following surface integrals of the diffraction, phi sub D, and radiation, phi, wave fields, and the hydrodynamic pressure, S sub B. To solve these surface integrals, knowledge of the velocity potential defined in linear wave theory is required. However, the boundary integral problem cannot be determined analytically aside from simple geometries. Alternatively, numerical approaches can be used. These solvers use a boundary element or BEM method to calculate the velocity potential on the wetted surface of the hull. The excitation force is the summation of the Froude-Krylov F sub Fk and scattering F sub S forces, and is expressed as the surface integral of the incident phi sub O and scattered phi sub S wave fields. The Froude-Krylov force results from the force of the undisturbed incident wave on the hull when the WEC is held still. Conversely, the scattering force acknowledges the effects of a disturbed wave when the WEC is held fixed. However, for small bodies relative to the predominant wavelength and are oscillating in heave, the scattering force is generally insignificant. The radiation force is a function of the WEC velocity and radiation impedance Z sub r. The impedance can be decomposed into a hydrodynamic damping coefficient B sub r and an added mass coefficient A. Radiation damping refers to the dissipated energy transmitted to the water that propagates outwards from the body. The added mass refers to the increase in inertia due to the displaced water in the area surrounding the body. The reaction forces include the summation of the PTO, F sub PTO, and mooring F sub M forces. The PTO force is the force from the reaction of the PTO components, and the mooring is the force on the WEC associated with station keeping. The PTO force can be represented in terms of a spring, K sub PTO, and damper, B sub PTO, but does not account for any PTO mass or end-stop mechanisms. The mooring force is proportional to the displacement of the WEC, where K sub M is the mooring spring stiffness. This representation, however, assumes negligible mooring mass, small amplitude motions, and that the natural period of the mooring is considerably less than the peak period of the incident wave. The simplified representation of the constituent forces acting on the WEC has been derived. Now they can be compiled and substituted into Newton's second law. Rearranging the resultant in terms of the complex velocity amplitude produces the following, where the PTO impedance Z sub PTO is the impedance of the PTO, and the intrinsic impedance Z sub I refers to the impedance of the WEC if the PTO were to be removed. The time domain model considered here is the integral differential Cummins equation used to describe the dynamics of floating bodies. It leverages the foundational assumptions of linear wave theory to incorporate contributions from the hydrodynamic, hydrostatic, reaction, and PTO forces into a model in the time domain. Considered here is a simplified form representing a single body constrained to motion and heave. Most terms have already been established in the frequency domain, but newly introduced is a convolution integral representation of the radiation force, an external force describing external forces acting on the WEC, such as the PTO or mooring. We will now explore the derivation of the excitation, radiation, and Morrison forces in the time domain, and you can now consider the causality of the radiation and excitation forces. The excitation force is defined in the frequency domain by the product of the excitation frequency domain function h sub f and the wave surface elevation eta, evaluated at the device centroid. The time domain equation for the excitation force can be obtained by taking the inverse Fourier transform and is written as a convolution integral because multiplication in the frequency domain corresponds to a convolution in the time domain. The excitation convolution is defined from -infinity to infinity, and the excitation impulse response function h sub e is non-zero for a finite period in the past and future, meaning that the bounds in the convolution cannot be reduced to that of a causal system. This suggests that both past and future knowledge of the wave surface elevation are needed to determine the instantaneous excitation force, indicating that the system is non-causal. So for the instantaneous excitation force, we need both past and future wave elevation. Although the bounds of the convolution extend to infinity, in reality only a finite duration of the wave elevation in the past and future must be known, because the impulse response will tend to zero over a finite time horizon. Water under the free surface is in a continuum, hence the pressure change due to the incident wave can be felt on the body before it arrives and lingers after it passes. The IRF dictates the causality of the excitation force. The system has a response prior to the arrival of the incident wave at the device location and after its passing. Obtaining the requisite wave elevation data must be considered. Past knowledge of the wave elevation can be easily accessed by measuring and storing the instantaneous wave elevation at the device location. The same cannot be said for future elevation data. Alternative methods must be employed to predict future elevation data, measure upstream waves, or bypass solving the convolution entirely, none of which are trivial. Morson's equation is a semi-empirical method to approximate the inline force on a body subject to oscillatory flow. The equation describes the force from the summation of the inertial and drag forces. Considering a slender cylinder with a small diameter d, with constant water density ρ, and a constant cross-sectional wetted area, it can be seen here. The inertial F inner considers the effects of the undisturbed and disturbed flow U over the cylinder. Furthermore, the drag force F sub D arises due to viscous effects and is proportional to the unsigned square of the flow velocity and can be shown as follows. The empirical drag C sub D and inertia C sub M coefficients are selected relative to dimensionless parameters such as the Hogan, Carpenter, or Kc number, where L is the characteristic length of the body and T is the period of oscillation. The Kc number describes the importance of drag forces over inertial forces for oscillating bodies and provides insight into which will dominate in Morson's equation. Aside from the linear radiation damping Cummins equation, um, Cummins equation does not inherently account for any energy dissipation. So if the Kc number indicates that drag is significant, the Morson's drag term can be included as a correction factor, especially if the device is operating at or near resonance. The hydrodynamic coefficients of the radiation force, the added mass, and radiation damping are dependent on the frequency of the incident wave field. At large frequencies, the radiation damping goes to zero, suggesting its inverse Fourier transform can exist. However, at large frequencies, the added mass goes to a non-zero constant, meaning that its inverse Fourier transform does not exist in its current state. Alternatively, the added mass can be decomposed into its frequency-dependent A omega and independent A infinity components, which allow the inverse Fourier transform to exist. Consider a WEC resting in static equilibrium with no incident wave field. Should the system be excited with an impulsive motion, a wave field surrounding the body would be produced. This wave field would then impart a force onto the WEC, which would then lead to motion of the WEC, suggesting that a past movement of the device affects the current motion of the device. As time passes, the generated wave field will propagate away from the body, and its effects on the WEC will decrease until all remnants of the initial perturbation have vanished. Furthermore, as the body was initially in equilibrium in calm waters, no force existed until the body was forced into motion, meaning that motion causes the force. The radiation force in the frequency domain is the product of the WEC velocity and radiation impedance, which have both been established. Now deriving the radiation frequency domain function h sub r that results from separating the frequency independent added mass from the radiation impedance. The time domain radiation force results from the inverse Fourier transform of the frequency domain equivalent, and no response exists until motion occurs when it becomes a finite real value. This suggests that the bounds in the convolution can be reclassified to correspond to that of causal system, and a causal system only requires past and present inputs, meaning that the convolution only needs to span from negative infinity to the current instant. The IRF decays to zero after a finite time horizon, suggesting that the bounds of the convolution can also be adjusted accordingly. Much of the difficulty in solving the Cummins equation arises from the presence of the radiation convolution integral. Therefore, finding alternative solutions has been comprehensively studied. Several methods have been devised to accomplish this, but only the frequency domain approach will be considered. The general form of the transfer function can be seen in the Laplace domain, where U is the input, Y is the output, M denotes the number of poles, zeros, and N poles, and A and B are parameters. Parameters A and B are determined by minimizing a loss function, which results in the minimum error between the radiation transfer function and the radiation frequency domain function. As the order of the radiation transfer function increases, so does the number of state variables in a state space form. Although higher order transfer functions may be required to fit the impulse responses arising from complex Hall geometries, it will significantly impact the realizability of solving the system in real time. A frequency-independent model using constant hydrodynamic is a second order ODE in the time domain with linear time invariant coefficients that correspond to two first-order equations in state space. The state variables are the WEC position and velocity, and the inputs are the excitation and PTO forces. Accurate applications are limited to monochromatic wave conditions as the assumption of constant hydrodynamic coefficients neglects their inherent frequency dependence. The frequency-dependent state space is similar, but instead of assuming the hydrodynamic coefficients as constants, it uses the radiation approximation to represent the frequency domain function. This can be condensed to a state vector Z, radiation state matrix A sub r, radiation input matrix B sub r, and can be accompanied by the radiation output equation Y sub r, the radiation output matrix C sub r, and the radiation feed forward matrix D sub r. Similarly, the inputs are the excitation and PTO forces, but the state variables include the WEC position and velocity, along with several dummy variables whose quantity is proportional to the order of the transfer function approximation. This is more involved, but allows for an accurate representation of WEC dynamics in polychromatic C conditions by acknowledging the frequency dependence of the hydrodynamic coefficients. We will just briefly reintroduce the intrinsic, PTO, and overall impedances before moving into complex conjugate control. However, since it was initially derived, the frequency-dependent and independent added masses are differentiated and the mooring spring stiffness removed. The largest velocity amplitude occurs for the overall impedance when the numerator is maximized and the denominator is minimized. Theoretically, the excitation force can be dynamically controlled by changing the Hall geometry. However, only the PTO dynamics will be considered here. The minimizing condition for the denominator occurs when the reactive components are eliminated. This condition can be satisfied by selecting the PTO reactance to negate the intrinsic reactance. Implementing this criterion forces the WEC into phase with the excitation force, imposing a resonant state, and this is the phase condition. The optimal conditions for power capture arise when power absorption is maximized. The optimal conditions are obtained when the intrinsic and PTO damping are matched, otherwise known as the amplitude condition. In summary, selecting the PTO reactance to eliminate the intrinsic reactance of the system and the resistance to match the intrinsic resistance enforces the optimum power absorption conditions. Complex conjugate control is a combination of the phase and amplitude conditions where the optimal PTO impedance is set to the complex conjugate of the intrinsic impedance. However, this analysis is only valid because of our harmonic excitation at a constant frequency, which allowed the treatment of the hydrodynamic coefficients as constants. The derivation of complex conjugate control has established the energy maximizing conditions in the frequency domain. However, real-time control with non-constant hydrodynamic coefficients requires the time domain equivalent, the inverse impedance formulation. The problem can be decomposed into three classifications regarding the causality and optimality of the system being described: causal optimal, causal suboptimal, and acausal optimal, but only the acausal will be discussed. Selecting the optimal PTO force in the frequency domain to cancel out the radiation frequency domain function. The PTO's radiation frequency domain function must be its complex conjugate. Since the radiation IRF is real, the complex conjugate of the radiation frequency domain function corresponds to a mirroring about t equals 0 in the time domain, and this results in a time-inverted radiation IRF. The conventional radiation IRF is affected by previous motions, meaning it has a memory effect that requires knowledge of past velocities. However, a time-inverted radiation IRF suggests that future velocities are required to determine the instantaneous optimal PTO force. Physically, this can be interpreted by the PTO requiring knowledge of future waves so that the corresponding radiation force can be produced to cancel out those waves. Three energy maximizing control strategies developed using these concepts will be examined: the Aalborg PID controller, model predictive control, and velocity tracking control. The mass spring damper representation of the PTO force takes their familiar form, a proportional integral derivative or PID controller, where MPTO is the derivative gain, BPTO is the proportional gain, and KPTO is the integral gain. The Aalborg PID controller circumvents the non-causality of the acausal optimal control force. The controller determines the desired velocity trajectory to enforce the velocity response of the WEC to be in phase with the excitation force. Assuming the WEC can be continuously held in phase, the energy maximizing conditions in terms of the instantaneous velocity and radiation damping can be used to represent the excitation force, eliminating the inherent non-causality of its convolution integral. After further manipulation, we introduce the optimal excitation force and a causal radiation force to the acausal control law, and the causal control law is produced. Model predictive control is a class of controllers based on numerical optimization applied for real-time optimal control. It uses a dynamic model of the system to generate state predictions over a receding horizon to determine the optimal trajectory while adhering to predefined constraints. Unlike the more traditional MPC objective function that determines the optimal trajectory to minimize the control effort and state error, the objective function wave energy elects to maximize energy capture. Furthermore, constraints can be used to enforce the physical limitations of the WEC, which are often related to the PTO force, WEC oscillation amplitude, and WEC velocity, as well as imposing the system dynamics. The system model often used with WEC MPC is the discretized Cummins equation with a radiation state space approximation. The state model includes previous states, position and velocity, the control action of the PTO force, and the disturbance, the excitation force. Previous states can be measured and the PTO force is being controlled, which presents no problem when computing states in the receding horizon, but the excitation force cannot be measured directly and is not explicitly known at future steps, nor can it be easily calculated. Therefore, methods to either predict or determine an alternative means to calculate the excitation force must be determined. This, along with significant computational requirements, pose challenges for implementation in real time. The velocity tracking controller determines the optimal velocity by assuming knowledge of the instantaneous excitation force and energy maximizing conditions. Assuming the excitation force is harmonic and narrow-banded, it can be represented by a harmonic oscillator. Defining the excitation force as the function of a single amplitude A sub e and frequency omega provides a means to determine those parameters given a known excitation force. Constant values of the hydrodynamic parameters are selected to model the system, and if the WEC is held in phase with the excitation force, the system model and optimal conditions can be used, leaving as only a function of the excitation force and radiation damping. The radiation damping curve is fixed for a given geometry. This suggests that the optimal velocity trajectory v sub ref can be determined given only knowledge of the instantaneous excitation force frequency and amplitude and the radiation damping curve. The architecture of the controller can be seen here, where the excitation force is treated as the input to the system and fed to an EKF to estimate the instantaneous excitation amplitude and frequency. The results from the EKF are then used to generate the adaptive control law, then that, along with the excitation force, is used to determine the optimal velocity. The reference velocity and feedback from the velocity state prediction are fed to the low-level controller to generate the control force needed to achieve the optimum velocity. The control and excitation forces are passed as inputs to the state model, which computes the predicted state velocity. However, the crux of this implementation lies in the assumed implicit knowledge of the excitation force, which is one of the greatest challenges for wave energy. The power conversion process is only considered the power absorption of the incident wave and the PTO reaction force, ignoring the intermediate steps in the PTO mechanism and the power regulation process. The primary interface or absorption process for a point absorber involves transferring the energy from the incident wave into mechanical energy in the form of oscillatory motion of the body. The second interface involves capturing the power retained by the WEC and is obtained by the PTO providing a reaction force opposing the oscillatory motion of the body. This figure shows the direct drive power conversion chain, where the second interface is a linear generator that captures the mechanical energy from the primary interface and converts into electrical energy. The third interface involves conditioning the electrical output of the generator, rectifying it, and then reverting it back to AC at the correct frequency before connecting to the power grid. Among these interfaces, several variables can be controlled to regulate the PTO reaction force. However, if a model-based controller is used, the existing hydrodynamic models must be extended to include all the systems up to that controlled input, thus adding complexity to the model and increasing the computational requirements of the controller. Now that we know where the PTO lies in the power conversion process, the working principles of a direct drive linear generator will be explored. Direct drive linear generators are well suited for the inherent reciprocal motion of ocean waves. Direct drive generators directly couple the moving parts of the generator and the power absorbing structure, reducing the mechanical complexity of the system by removing intermediate power conversion steps. Although linear generators boast significant theoretical potential, physical challenges have plagued their unconventional design and have limited their applicability to the test bench. The fundamental mental theory behind linear generators will now be explored. A linear generator contains two general components, a stationary body, the stator, and a translational body, the translator. The stator is found with a conductor, the armature windings, and the translator is equipped with permanent magnets mounted in alternating polarity. The changing magnetic flux from the translational motion of the permanent magnets on the translator about the stator coils induces an electromagnetic force, or EMF. Should this induced voltage be connected to a load, it will prompt current to flow. This current then generates a magnetic field that opposes a change in flux by creating a back EMF that acts on the translator. This concludes the overview of my final presentation for ECE 6013, overview of Oceanic Wave Energy Conversion. I'd like to thank everyone for attending today. On the floor to any questions.